Hi. So yes, long story, I'm Tamas, and I work for Troops as a software engineer, and I'm going to talk about monads a little bit and how they can make your life a tiny bit better. I've been doing Scala for the past 7 years. I really like functional programming. I'm not very good at it, but I like it. I like to sneak it in whenever I can, even if it's not necessarily the main direction. As it was mentioned, I work for Troops, which is an up-and-coming startup here in New York City. We are growing fast, and we build AI for sales and marketing teams. And obviously, we are a Scala shop. Just let me know if this sounds familiar. You start a new project, you have some great idea, you have a clear path how to reach that idea, you know how you're gonna write your code, you have a small team of 1 or 2 people, you review each other's code, everything is neat, everything is clean, like the barriers are in place, like you're just very happy and everything is going great. But then things start to get bigger. You hire more people, your code base is getting bigger, you have a product team that's breathing down your neck, you have to develop 5 different features at the same time, you're working on many things, you just no longer can pay attention to every single detail. Like, you have some conventions in place, but things start to diverge. Everybody is doing their own thing. It's a little bit different for everybody. It starts to get a little messy. And then you're in support, and you have to figure out some support issue. You're tracking down a bug. You look at some feature that's totally unfamiliar to you. It was worked on by somebody else. So you look at the code. You look at the logs. It gives you some information, so you go back and look at the code that emitted that log message, and you get something like this. It's probably not super helpful. So what can you do next? You look at the function that emitted this log message. You look at try to figure something out from the context. So you have a function that looks like this. You have a return type that's not exactly tells you much about what's happening here. It gives you a number or not. You're gonna get it at some point in the future. Like this is just an example. This is just a couple of lines, so you can actually read through it. But imagine this is like a gigantic wall of code. You see some log error messages. So obviously something is going wrong, but you're not sure what can you do it. So you have your team, you have your problem, you want to do something about it. There are some tried solutions that you can reach back to. You can try to use an opinionated logging framework that would force you to log information a certain way. It can work, but it's not ideal. It may or may not work with your other dependencies, like they might rely on other logging facilities. You might have a problem matching them up with each other. Or you might even have to go back and refactor everything just to make things work. You can try to review everything. That actually seems like a good solution for like a small-ish team. It usually seems like a good solution longer than it actually is. But it just eats up all your time. It just doesn't care. Like you cannot review all the code coming out of a team of 50. So that's not gonna work. You can write extensive guides for everything. Like you can have a code style guide, you have a best practices guide, how to do logging, how to handle errors, all these things. Again, this is something that can work, but as the number of features grow, it's going to be harder and harder to maintain them, and you have to maintain them. That's also a problem. You can do training. You can train all new employees. That's great. That's a great team building exercise. But again, things are going to start to diverge soon after you're done training. So maybe that's not the best solution. So there should be a better way. And I think there is. You can build that into your code using more functional paradigms. So what do we want to achieve? We would like to push best practices that we already have on our team. Like we want to make sure that the things that we came up with, the solutions that we came up with, we keep using and we don't have to take a totally different direction. We want to take care of things that you don't really want to worry about while you're working on your business logic. You don't want to think about how to handle errors. That should be given at any given time. The same goes for logging. Like you need good logs when you're debugging an error, but that's the least of your worries when you're developing a new feature. It should be just standard that just works. You should encourage people to use expressive types. They should tell others what they want to do with their types. It should be descriptive of what's going on. You can have something like this. It's perfectly serviceable. It holds information, after all. But without knowing what's behind those question marks, you don't really know what's going on. Like it's companies, but what is the integer, what is that string? Just tweaking it a little bit, giving it more information already helps. Just even if you just use a few type aliases, can help to make things much better. You want to make sure that you're not forcing people to drop everything and start using your wonderful new library or new approach immediately. Like it's probably not even possible. They have to work on their features or they have to move the product forward, but also it's just too much work and also it would require a big leap of faith and potentially a steep learning curve, which you also want to avoid. Like you want to create a nice way in, something that's just easy to start to use and then get things better. We already made some progress in fixing these issues in our code base even before we standardized on anything. Just to give you an example, we had this nice little wall of code where we were returning futures of eithers from an API or a database call. It doesn't really matter. It's basically means that this thing is asynchronous and also it can return an error. So we had to handle the errors and we had to then have a subsequent call that also returned a future of either or something. It requires nesting. It's hard to read. It's hard to understand. You don't have to. Don't even try. That's not the goal here. So what we did is that we started using cats. For anyone who's not familiar, cats is this library that allows you to do more functional code in Scala. It's so here we're using the either t monad transformer to just basically cut down on all the nesting and made the code easier to read. And if somebody comes in, it's just easier to understand what was going on. You can focus on the actual business logic instead of having to read through lines and lines of error handling and unwrapping and wrapping different data structures. Another example is that of making progress is logging. Like it's a little bit artisanal. It's handcrafted. It involves a lot of manual work, but it gets the job done. We have our context and we have our error message. Again, every time you create a log message like this, you have to think about it. Like you have to think about it. This is how we do logging. This is how you're supposed to do something. That's just a convention. Nobody's gonna force you to do that unless you actually type it out and somebody complains during code review. So we took the next step. And this next step is called tres, which is short for troops results. It's just a small library that standardizes on a return type for functions. We have data flowing through our functions. This is a standard way to hold onto that data. It takes care of logging, so you don't have to worry about it. You just enter the logs a very specific way, and then it's going to be there. It's going to accumulate it for you. It enforces error handling. You have to think about it. It's built into the type. You cannot just ignore it. You cannot just say that like something is going to happen and it's going to be all right. It's still built on top of cats. It makes sense to us. We're already using it in our code base extensively, so it was the logical choice. It's tiny. It's less than 100 lines of code. I'm not suggesting anyone to actually use this library. I'm suggesting to just write a library like this for yourself. I rewrote it 3 or 4 times just by thinking about it and trying out different approaches. It's really easy. Once you have the basics down, it's really easy to just test different approaches and tailor it to your very specific needs and your teams and code bases very specific needs. I said it's small. It's basically a type alias. Like that's at its core, and then a few type classes and a few helper functions to make it easier to use in our existing code. And it built on top of monads. So first, let's look at how we use it. So let's go back to our nesty function that just logs left and right and then returns an option and turn it into this. It's a little bit longer, but it gives me a lot more information. First, it gives me a nice error type that I can match on, that I can later expand. If I have a new error type, my compiler is going to complain that why am I not dealing with it? It gives me an error, a log message that I can create relatively easily. The as error is just this this implicit class that you can use to expand your data with a few helper methods. I'm going to show it later. And then we have these rich contextual information helper methods that we can use to add the context in a standardized way. So this, again, this very manual thing becomes something very similar, but something that's gonna always look the same, and it can be controlled independently from the creation, how it's gonna be pushed into the whatever log facilities you're using. So let's look into how monads come in the picture, how they can help us. So first, they hide stuff that is external to your business logic under the hood. You don't have to worry about them. It gives you the opportunity to just focus on your domain and your data, and don't worry about things that are external to that. It's really compact. As I said, you can just write and rewrite it as many times as you want. You don't even have to use a library. Like, as long as you have some kind of function that you can use to create the data structure and another function that you can use to collapse them into each other, you're basically done. Still, I would prefer to use a library because you get so many nice things and the performance is going to be probably better. So I would still go with that. Because if you can build, there's an ecosystem there already that you can use and you can build on, and it's nice, and it makes it really easy to use and gives you access to great documentation that you can rely on. And it fits into code that's not very functional. Our code is not super functional. We have some functional paradigms present in our code, but it's pretty old school imperative code. Still, it works great. It's very compact. It doesn't require a huge shift in thinking to start using the API once it's available. So how do monads work? I'm gonna take a very practical approach to this, more like how we use them. So they are data types that hold other data types. They wrap around your data, and you can execute actions, computations on that data. For example, option is a monad that can hold data or not. That's what it gives you, the context that it gives you the option of not having data. All the smarts is built into the structure. You don't have to think about having or not having data once you're using options. Obviously, it's built into the logic. It's composable. You can have multiple options, one after the other. They're gonna know when you can step to the next one. It's gonna be built based on how the structure is built up. So for example, if you have you can use the flat map on an option. It will take the value from the previous option if there's one, and then it can do something with it and return the new option. That's basically these are the two important functions that you need to implement to have a monad. The first one is also called a pure function or a unit function, and then the flat map is also the bind. So to look at an example in more detail, here's again, we have two options. Both have a value, 7 and 5 respectively, and then we use a for comprehension to first extract the first number and then the second number, and then return an option of the sum of the two. The for comprehension is just a syntactic sugar over flat map, just for clarification. These statements are executed sequentially. You don't touch num2 until n1 is extracted. If you don't have n1, so for example, if num2 is, so if you don't have n1, you're never gonna reach to num2, and if you don't have any of these, the whole thing is obviously not gonna return anything. Again, this is something that option takes care of. Just a simple example. Like, there are other monads in the Scala API that are very well known, like list, which is obviously holds a number of items, either that gives you the option of an error type, or even future that gives you a value that is not there yet. It's gonna come later. Sometimes you want to combine these different behaviors, and you wanna create something that can support more of these effects, not just one. So you want to wrap these monads into each other, which obviously you can, since a value that it can hold can be another monad, and you can create monad like stacks of monads. So you have your monad stacks where each layer, in this case, it's a future of either, is stacked up, which supports two different effects. One is the future that makes the future monad gives you an asynchronous value that is not available yet. It's just a promise of a value, and either, which can be an error potentially. So it combines two different behaviors. There's one painful thing about having these stacks. This is a small stack, but obviously you can have many, many more on top of each other, is that you have to build the whole stack up every single time you're creating something. So I have this very simple function that just gives me a number that gives me a number in this data structure. And I have to do every single layer. If I would have 5 layers, I would have like 5 different functions. It's not the prettiest thing to do, but you can deal with it. It's not terrible. When things get a little bit worse is when you have to work with that data. It's very similar to that first code slide that I showed about before we started using either T. Basically, you spend a lot of time wrapping and unwrapping data in and out just so you can have access to it and somehow deal with the errors. It's not pretty, especially because probably you're going to do this a lot more than just creating the data. Like you'll probably load the data once or in a couple of functions, and then you have your business logic where they use it in several different situations. So monad transformers come to your rescue. Monad transformers are versions of monads that allows you to combine multiple monads into one and treat them as one. So this stack, the future of either, will just become either T of future of E and S. This is either T, this is coming from cats. It's basically an either that also can be combined with another monad, in this case future, so you can have both effects while directly accessing the value inside. So this getNumber method turns into this equally simple method. You can just use either T's pure method to create the same data structure. It's going to work because as long as future, since either T has to be combined with another monad, either T can pull in the appropriate value to create a future that then will lift it in the either T. So this getSum method that I said is a little unwieldy, becomes a lot easier to read and a lot easier to write in most situations. There's one last piece that I wanted to mention before I go to more concrete examples, and that's type classes. It's a slightly different topic. It doesn't directly build on monads. It's something that is important because it kind of encourages you to use types as specifically as you can. So it's really nice to have people use type classes to express specific behaviors instead of using very generic types. I'll show that in a little bit more detail later. So what can you do with type classes? First, when you want a specific kind of behavior, you define that behavior. In Scala, you create a trait that describes the functions that you want to be able to use with a type class. Then you start to expand the functionality of existing data types by creating implementations of the type class for that data type in a way that the compiler can later find, mostly using implicits. That's great because you can just mix and match things. Like you're not tied to either creating a new functionality or the new data type. You can do that anywhere. Even though it's better if you do it either where you're creating the new functionality, like usually you define type class implementations for very generic types where you're creating a new functionality, or you do that where you're creating the new data. And the compiler will take care of the rest as long as you have them in scope. Like you use implicit resolution to do this, so you don't have to do anything in runtime. It's going to be there when you need it. To look at an example, this is as simple as it can get. It defines a type class of data that always has an int. So it can always return an integer. This is going to be satisfied as long as you have a getInt method that returns an integer. I created an implementation for option of int. It either returns the integer that's in the option of int or returns 0 if the option was empty. And once I have these, I can start using my type class. Any A type will work in this setup as long as I have an always has an int, and I'm going to be able to create a sum of the values in my list. So it's really easy, and it kind of forces me to think about my functionality in terms of types, not so much in terms of like ad hoc functions. So if I try to run this, then I'm just going to get back a number, just like nice and easy. But if I try to do this with strings, I'm going to get an error message from the compiler. So it couldn't pull in the appropriate implementation, so it's not gonna run. So how did we use all these things in our library? So as I said, its core, it's just a type alias. It's an either t of writer t of f, a vector of logline, and e and s. The either t is responsible to handle a potential e error type. The writer t is responsible to accumulate error messages. In this case, a vector of log lines. Log line is this case class that I'm going to show later. It's a little long. We almost never use this particular case. We have a very simple version we have called tres that is just the original tres-t with the in place of the f monad, we plug in the id monad. The id monad is just a type alias that points back to itself. It's just a trick that allows you to attach a bunch of type classes and the implicits on the id monad. So you can use it in place of a monad, but it's for all intents and purposes it's transparent. You have your value there, and that's it. And then we have our asynchronous tres version that has a future monad plugged in there in the middle. So this is what we use most when we talk to database or some external client. Since this is just a type alias to a bunch of cats classes, we get a ton of functions for free. These all work, like all the standard stuff, like exist and flat map and fold, these all will work. I didn't list all of them because there are dozens more, but it's like there are a couple that you just get them because you have, they come from cats for free. Still, we created a few custom functions, especially on the object itself. So creation, like data structure creation, is easier, and more importantly, it matches our existing code base. So we have some generic methods to create the data types. It builds on existing use cases, going through the code and make sure that everything is in there. We have some stuff for very specific data types. Again, it's kind of redundant, but it makes it easy to adopt the code for people who never seen it before. The from action is basically, it's a little bit different because that allows you to catch all exceptions and wrap it into this data type. So everything that's in there is safe, and you don't have to worry about that later. That's actually important at times. And then we have a few special methods that we use to create empty structures that are for the purpose of logging. So this is by the return unit. Like they don't hold any data other than they add a new line to the accumulated log list. The log now is a kind of an escape hatch. It's a workaround that you can use if you have a logger in scope to immediately send out a log message that can be useful sometimes when you don't want to wait until the end of your run to emit the logs. We also attach some methods to the instances, like error map, for example, which is identical to left map that already exists. Again, it's something that just makes it easier to adopt because it's something familiar to the people. And then we also have the same log where you can just run it on your existing data and add the new log message. And then we have like these nice methods like log on failure and log on success that lets you expand your log messages in cases that are very common, so you don't want to necessarily match on them. It's easier to just use these helper methods. And then finally we have render that lets you exit this whole structure, like render your data, log whatever you have to log, and get to your end result, which is, say, an HTTP response or a string if it's like a console application or something like that. So just the last step, it's, I don't know how visible it is, but it's like, that's the case class that holds the log messages. It's the standard stuff, like log levels and the message. We use the source code macro to propagate file and line and class information in place, so you don't have to worry about that. Also, we save the timestamp when the object is created because, again, it might be logged later. And then there's the in method that I showed before that provides the way to add context. Context is key value pairs of information where the value is something that implements the context item type class. That is, again, as easy as it can get. It's just a way to convert it into a string. So it's automatically going to work. Another type class that we use here is loggable. That is, as long as there's an implementation, it lets you your data type to convert into a log line, so like a log message. And any data type that has an implementation for loggable can use these as error, as warning, as info, as debug methods. So you can just say, whatever is my string dot as error, and that's going to be a log message, which is pretty convenient in most use cases. So how can you use this? First, let's define some error types, because that's what we want to do in the first place, to have something that expresses what's going wrong. So I have my getNumber function. If my number is even, I'm good. I just return the number. If it's an odd number, that's an error. So I return an odd number. Error, again, is something I can later match on. I think it's way more convenient to use this than just have a string and then wonder what's going on as a return type. So you have this function, and then you have your service. My service is going to sum up numbers, so I'm going to have my sum error. That's probably my error type is specific to my service, so you have a group of functions that gives you a service, and that has probably one error domain, and you want to list your errors there. So here I have my getSum function that takes the get data from the getNumber function. I use the error map to convert between my error domains, so to make sure that I have the correct error type. It's not terribly pretty, but it's one extra line, and it allows you to, or actually it forces you to think about how you're transferring that information that something went wrong from one domain to another. So I think it's useful to think about. Also, another thing is that if I have a new kind of number error, my compiler is gonna give me a warning. So I'm gonna for sure, well, not for sure, but hopefully I'm gonna handle it. I'm not gonna just leave it there. And then finally, if I wanna run it, I just call render on it, and it's gonna be, in this case, converted into a string. Again, I didn't pass any functions to render. It's all handled through types. So just a reminder, this is how render looks like. It requires a value extractor type class and the presence of a logger. This is the first time that you actually need a logger unless you use log now. That's also an important and nice thing, that you can have your business logic. You don't have to worry about logging. There you are just passing data. And then this is your value extractor implementation is pretty much a fold that either takes your error type or your success type and converts it into whatever output type you have. This seems like a lot to do every single time, but mostly your output type is fixed. It's the same in every situation. It's like whatever you want to return to through your framework, say play. Your error type is the same for your problem domain, so it's going to be, again, fixed. Maybe you have 5, 6 in your application, not that many, and then you have your output type, but usually you already have some way to serialize that anyway, so you have to think about that already. For example, if you have play and you use plays JSON writers to create JSON, you can just write an implementation that's going to work for everything that supports JSON through plays library. to also support loggable and value extractor. So I think it's already a big improvement on what we've been doing. It's standardized a bunch of our best practices. We just kept doing what we've been doing already, only a little bit better. Obviously, there are some trade-offs to everything, to this too. One is that exceptions can break the flow. Like, since you're collecting your log messages all the way to the end, if you have an exception that is not caught, that can mess things up. You're never gonna get your log messages. Log now can work around it, but that's a problem. Ideally, you don't want to have exceptions. You want to make sure that whenever something enters your code, it's exceptions are code already. So that shouldn't be an issue, and in practice, it's not really an issue. You have to be careful with memory usage. It's, again, if you have a lot of messages, like thousands of lines, tens of thousands of lines, or you're serializing large objects, that can add up. That can be a problem. So that's something to look at. Again, your mileage might vary, but it's something to be aware of. Sometimes you can get really confusing error messages, at least confusing for me. Your types get big, and you get something like this. I mean, I highlighted the errors. What was the problem? It was actually that I wasn't using a type hint. So I was looking for a read error type, and I got a not found type. And it's big. And it's not necessarily thrown where you should put the type hint. It's more like thrown where the compiler just got to the point that, yeah, it doesn't make any sense anymore. So that leads to the other thing, that sometimes you have to add more type hints that you would add otherwise to help the compiler figure out what's going on. And IDs just give up. Like, they're not gonna work in a lot of situations. So I'd like to thank you for Dustin and Workbench, so I could talk about it. And thanks for my very patient coworkers who listened to many versions of this talk before. Thank you.